We saw how reaction rates depend on the concentration of the reactants with our method of initial rates, but we may also be interested in how concentration varies with time. So consider the reaction, reactant A yields products. If our reaction is first order, then our rate law will equal rate equals K times the concentration of A. And since this is first order, our exponent equals 1. When you graph the concentration of A on the y-axis versus time on the x-axis, the decay is not linear, but rather exponential. The best fit is a curve and not a line, which makes it hard to calculate the concentration of reactant at a given time point. In order to achieve a linear fit, we use what's called the integrated rate law, which is literally the integration of the rate law. Using calculus, you can determine this reaction. And what you end up getting for a first-order reaction is that the natural log of the concentration at some time t equals negative the rate constant times time plus the natural log of your starting concentration. The starting concentration is indicated by this subscript 0. When you graph the natural log of A versus time, the result is a linear fit, whose slope equals negative k. As you can see, your integrated rate law is in the form of y equals mx plus b. And this is actually really useful for determining concentration at various time points. A specific value of time, called the half-life, is also studied when it comes to rate laws. A half-life, or T1/2, is the time it takes for the concentration of a reactant to decay by 1/2. If we consider a first-order reaction, where concentration of A is graphed on the y-axis and time on the x, if we start with 16 molar A, after 1 half-life, it is decayed and there is only 8 molar. After the second half-life, there's 4 molar, and the third half-life, 2 molar, and so on and so forth. What's unique to a first-order reaction is that all of these T1/2s are equal. So the first half-life equals the second half-life, which equals the third half-life, and so on. And for a first-order reaction, T1/2 will equal 0.693 divided by the rate constant, K. This table simply summarizes the integrated rate law for a first-order reaction, where our rate law is rate equals K times A, our concentration time equation involves the natural log, and our linear graph is the natural log of concentration versus time, where our slope, negative slope, equals our rate constant, and our half-life is 0.693 divided by the rate constant. Now let's consider a second-order reaction, in this case, the decomposition of NO2. So since it is second order, our rate law is going to equal rate equals the rate constant K times the concentration of NO2 squared, since it's second order. When you graph the concentration of reactant on the y-axis and time on the x, you do not get a linear fit. Furthermore, if you graph the natural log of concentration versus time, you do not get a linear fit. You get a curve. This tells us that the reaction is not first order. Finally, if we graph 1 over the concentration versus time, we end up getting a linear fit. So the integrated rate law for a second-order reactant is given by this equation, where 1 over the concentration at time t equals the rate constant times t plus 1 over the initial concentration of reactant. In this case, the slope of our line equals the rate constant K. The half-life for a second-order reactant is different than first-order, as not every half-life is equal. This is because it depends on the initial concentration of reactant. If we look at the graph where concentration of reactant is on the y-axis and times on the x, if you start with 16 molar, again, when you go through one half-life, you have 8, then 4, then 2. However, since this is second order, you'll notice that the second half-life is longer than the first. The third half-life is longer than the second. More specifically, each half-life is twice as long as the previous. For a second-order reaction, then, your half-life, or T1/2, equals 1 over your rate constant times your initial concentration. This table now summarizes the integrated rate law information for a second-order reaction. The last kind of reaction we need to consider is one that is zero-order, where rate simply equals the rate constant K, as the exponent of the reactant is 0. Zero-order reactions are actually rare, but what is nice about them is that you obtain a linear fit when simply graphing the concentration of the reactant versus time. And in this case, your integrated rate law is going to equal concentration equals negative K times T plus the initial concentration A, where the slope of your line actually equals negative rate constant. Now this table summarizes the integrated rate law for a zero-order, first-order, and second-order reactant. Let's walk through a problem together where we utilize these integrated rate laws. In this case, the decomposition of sulfuryl chloride is a first-order process, and we have a rate constant of 4.5 times 10 to the negative second. If we begin with an initial sulfuryl chloride pressure of 375 torr, what is the pressure after 65 seconds? In the case of gases, we can use pressure in place of concentration. So since this is a first-order process, we'll use the integrated rate law for a first order. In this case, the natural log of the pressure at time t is going to equal negative the rate constant times t plus natural log of the initial pressure of our gas. Let's substitute into our integrated rate law equation the information we know. We know our rate constant, K. We know our time, 65 seconds. And we know our initial pressure, 375 torr. So if we plug and chug, the natural log of our pressure after 65 seconds is going to equal 3.001926026. Remember that for a natural log, the base is E. So to solve for the pressure after 65 seconds, you raise E to the 3.001926026 power. So in this case, the pressure of sulfuric chloride after 65 seconds is going to equal 20 torr. The second part of this question asks, what time will the pressure of sulfuryl chloride decline to 1/10 its initial value? So let's write down what we know. So we want to know the time t where pressure equals 1/10 its initial value. So we know this is first order, so we're going to use our first order integrated rate law equation, and let's fill in what we know. So we know the pressure at our time t is going to be 1/10 the initial. We know our rate constant, we're solving for t, and we have our initial pressure. Now, let's do some algebra to solve for t. In this case, you're going to take the natural log of 1/10 the initial pressure minus the natural log of the initial pressure, which equals your rate constant times T. If you recall from algebra, when you do a subtraction of natural logs, you can actually write it as a division. So in this case, our P initials will cancel. And when we simplify this, the natural log of 1/10 is going to equal our rate constant times T. So if we solve for T, we end up getting 51 seconds. So after 51 seconds, the pressure of sulfuric chloride will be 1/10 of its initial value. Pause this video and do the following practice problem using integrated rate laws. For part A, you should have calculated a concentration equaling 1.2 times 10 to the negative 7th grams per centimeter cubed, and for part B, a time of 0.35 years. Let's walk through a practice problem using the second-order half-life equation. A reactant is involved in a reaction, which is second order. It decreases in concentration from 16 molar to 4 molar in 300 seconds. So how long does it take for its concentration to decrease from 4 molar to 1 molar? I will walk through two methods of doing this type of problem. In this case, since we're dealing with a second order reaction, our T1/2 equals 1 over the rate constant times the initial concentration. Let's think about what we know. We're told that to go from 16 molar to 4 molar, it takes 300 seconds. In this case, 16 to 4 is actually 2 half-lives. So the first half-life plus the second half-life is going to equal 300 seconds. Now, since this is a second-order reaction, we know that each subsequent half-life is twice as long as the previous. So our second half-life is going to equal 2 times our first half-life. So if we substitute 2 times T1/2 1 into this equation, we get that our first half-life plus 2 times the first half-life will equal 300 seconds. So 3 times the first half-life equals 300 seconds. So our first half-life, going from 16 molar to 8 molar, is going to equal 100 seconds. So if we go back to our half-life equation, we can substitute in 100 seconds for our T1/2 and 16 molar for our initial concentration. And then, if we solve for K, we get our rate constant equals 6.25 times 10 to the negative 4th. Now that we have the rate constant, we can use the rate constant and initial concentration to find the half-life for the decay of 4 molar to 2 molar. In this case, the half-life is going to equal 1 over our rate constant times our initial concentration, which is 4 molar. That gives us a half-life of 400 seconds. The half-life going from 2 molar to 1 molar will equal 1 over the rate constant times the initial concentration, 2 molar. So that half-life equals 800 seconds, which is double the one before it. Since the problem asks how long does it take for the concentration to decrease from 4 molar to 1 molar, you need to take those two half-lives we just calculated and add them together. So in this case, 400 seconds plus 800 seconds equals 1200 seconds to go from 4 molar to 1 molar. The other method for solving this type of problem involves recognizing the fact that each half-life is twice as long as the previous. So using the original math we did, where we found that our first half-life is 100 seconds, we can determine each subsequent half-life by doubling. So from 16 to 8 molar, it's 100 seconds. For 8 to 4, it's 200 seconds. 4 to 2, 400 seconds. And 2 to 1, 800 seconds. For this problem, the half-lives we care about are the 4 to 2 half-life and the 2 to 1 half-life. So again, since we want the time for it to decay from 4 molar to 1 molar, we take the half-life of 4 to 2, which is 400 seconds, and add it to the half-life for 2 to 1, 800 seconds. And we get the same answer as in our other method, which is 1200 seconds. Pause this video and do the following practice problem on a first-order half-life. You should have calculated that for this decomposition, the half-life equals 9.9 times 10 squared seconds. That was our video on integrated rate laws. Be sure to go do your warm-up quiz on Moodle.